Hello everyone. So we are actually continuing our solved problem on 3D Cartesian vectors. This is the second part of the problem. It's a slightly shorter part than the previous one, so I just wanted to break it into two pieces. Okay. Here is the problem so far. I'm given all these forces F1, F2 and F3. Find the resultant vector. Okay, so I request you to consult the part 1 of this video for finding the resultant force vector. Okay, so from part 1, of this problem. Okay, we found out the resultant force vector, which is Fr, which was F1 plus F2 plus F3, and after you went through some geometry and some number crunching, Fr ended up being the following. So Fr was 225i, okay, and 315.6J and 160K. So many newtons. Okay, this was from part 1. Okay, this was obtained in part 1. Of the video. Alright, what's our aim now is to obtain the coordinate direction angles of the resultant vector. Of Fr. Okay, and I'm going to call them as alpha r, beta r and gamma r. Okay, and how to find that. Okay, so first step is first of all write the magnitude of Fr. Okay, so okay, how to find the magnitude? Since it's a Cartesian coordinate system, you can do the sum of the squares and take the square roots of the components. Okay, so in a Cartesian system, we can see that Fr is going to be 225 square, the magnitude of this one. Okay, 225 square, 315.6 square. Okay, and then 160 square, the square root of all of this. Okay, which will tell me that Fr without the arrow, which is the magnitude of this guy, is going to be approximately 419.3 newtons. Okay, so this is the magnitude. Alright, fantastic. So we have the magnitude. Then what do? My next step is to write the vector in the standard form. Okay, what's the standard form? Okay, so first step is find the magnitude. I guess I need to bring this a little down. Okay, so find the magnitude, then write it in the standard form. So what's the standard form? Here is the standard form. Okay, Fr is going to be an x component of Fr, which is Fr times cosine alpha r in the I direction, Fr times cosine of beta r in the j direction, Fr times cosine of gamma r in the k direction. Okay, this is the standard form, and then compare this standard form with the actual answer that you have obtained. Okay, then compare. Okay, and compare the standard form with the numerical answer. Okay, and I'm going to write that right underneath here. So the numerical answer that I had was, this was 225i and then 315.6 J, and I had it as 160 K, so many newtons. And it is fair to see the following. Okay, the quantity that I have underlined here is going to be the same as the quantity that I have here, because these two vectors are the same, right? Likewise, the quantity that I have underlined here is going to be the same as this particular quantity. And likewise, the third quantity that I'm underlining here, which is this guy here, is going to be the same as that quantity there. Okay, so just by comparing the two, we end up getting the following. Fr, cosine of alpha r, is equal to 225, which tells me that alpha r is equal to cosine inverse, of 225 divided by Fr, which is cosine inverse of 225 divided by 419.3, and so alpha r, after I do the crunching, is going to end up being approximately 56 degrees. Okay, so that's the first answer. And then I do the next comparison. Okay, Fr, cosine of beta r, is equal to 315.6, which tells me that beta r, if I skip a couple of steps, okay, beta r is going to be cosine inverse of 315.6 by the same magnitude, 419.3, or beta r is going to end up being around 41 degrees for me, approximately. Okay, and then lastly I have the third one, which is Fr, cosine of gamma r, is equal to 160, which implies that gamma r is inverse cosine of 160 by 419.3, which tells me that gamma r is approximately 68 degrees. Okay, this is something very useful for us to know. Okay, and I want to make a very brief note here. Okay, a quick digression in a sense. Okay, so digression. Suppose we have a vector f is equal to 120i minus 160j plus 140k newtons, and we need to find beta r, or beta. Okay, let's just say beta. Okay, how to do so? And what do you have to do for that? Okay, you have to first of all write the vector in the standard form. So compare the numerical answer with its standard form. Okay, and what is the standard form? F is f times cosine alpha I cosine beta j cosine gamma k. Right, and since I need to find only beta, if I do the comparison, it is quite obvious to see that this entire thing will be the same as that entire thing. So if I do the comparisons between these two, okay, I end up getting the following. F times cosine of beta is equal to minus 160. So the thing is, do not forget negative signs if you see them. Okay, that was the main reason for showing it. So I just wanted to show you that, okay, hey, there is a negative sign. Okay, and if you see a negative sign, do not forget that. So this is a digression. This is not related to the problem, so I'm not going to go and stress on this, but this was something that I wanted to discuss. And essentially the idea is, okay, how do I find the coordinate direction angles? All I have to do is write the vector in its numerical form, which is shown right here. Write the vector in its standard form, which is shown right above there. Then compare the I components, the j components, and the k components to get the vectors alpha, beta, and gamma. So my final answers are the following. Okay, so which means that I have vector fr. So back to our problem, sorry. We have so many problems, right? All right, so back to our problem. So we obtained fr as 225i, 315.6j, and 160k newtons, and alpha r was approximately 56 degrees, beta r was approximately 41 degrees, and gamma r was approximately 68 degrees, and the magnitude of fr was obtained as 419.3 newtons. Okay, and my last thing is to draw this vector on the Cartesian frame. Okay, that is the very last thing I want to do. So draw vector fr in the Cartesian system. Okay, how do I do that? Here is how I do it. Okay, first step is this. Okay, I see that if I write fr as frx, fry, frz, then just by direct comparison, frx is 225 newtons, fry is 315.6 newtons, frz is 160 newtons. Okay, then which means, and these are all along the positive directions because alpha, beta, and gamma are all positive. Also notice that all the components are along the respective positive axis, because alpha r, beta r, and gamma r are all acute angles. Okay, that's something that I want to underline. This is because all of these are acute angles. Okay, so which means this is fairly easy for me to draw. Okay, so and here is what I'm going to be doing. I'm going to be drawing my Cartesian XYZ coordinate frame. Okay, so this is the x-axis, and then this is the y-axis, and then this is the z, of course not in the order that I just mentioned, so x, y, and then z, and then I'm going to start drawing. Okay, along the x-axis I'm going to have an frx. Okay, so this is going to be a magnitude of 225 newtons. Okay, then along the y-axis I'm going to have a force which has a magnitude of 315.6 newtons, right? This is actually the y-axis. Somehow it morphs into something else here. I want to make sure that I'm drawing the axis, and I'm also drawing this force here. Okay, this is the y-axis, and then here is what I'm going to do. before I draw the z component, of course I know that the z component is directly sitting up here, and that's around 160 or something, so not drawn to scale, but you get the idea. So that's around 160 newtons. Now how do I complete the parallel pipette is by first of all saying, okay, I'm going to draw, maybe I'm going to use a different color here. Okay, so I'm going to draw a line this way. Okay, align it with the head of this arrow here. Okay, and then continue on, and then align it with the head of that arrow there. Okay, and then I have to draw a 160 Newton arrow, which is straight down here, right? And once I'm done with that, then I can kind of construct or reconstruct the parallel pipette. So this is also going to be the same magnitude of 160 newtons. Okay, and to get the actual force, let's complete the parallel pipette in a way. This is going to be confusing to look at, but hopefully not too bad. Okay, so I'm going to draw that. Then I'm going to join these two. Okay, I'm going to join those two as well. Okay, then I'm going to have one more. Okay, somewhere here. Okay, and then join these two, and then join those two, and then my resultant is going to be starting from here all the way down to there. Okay, so that is going to be my resultant, and I'm going to take an arrow and then draw it as FR, which is the magnitude of the resultant, and that was around 419.3 newtons. Okay, so the parallel pipette is drawn in the manner that was shown, and this component here is the FRX component. Okay, and then this component here is the FRY, and then this guy here, which is the 160, is FRZ. Okay, and this is typically how you will recreate these vectors, and we'll keep doing this for different other problems as well. All right, thank you very much for your patience. I will see you all in the next concept talk. Bye bye.